Hi everybody, in this video we're going to continue our work with optimization problems, section 12.3. We had done the example regarding the profit equation and finding the maximum, the largest profit. And so we had started to talk about these box equations. So a watch manufacturing firm needs to design an open top box with a square base. The box must hold 32 cubic inches. Find the dimensions of the box that can be built with the minimum amount of material. So we kind of have started to work through some of these, but I wanted to talk about it more in depth. So I have copied the problem here, and we're going to start from the beginning. So some of the keywords, always focus on what is it that you're trying to do? What is the task? What is the question? So in this case, the question is we want to find the dimensions of the box that can be built with the minimum amount of materials. So this is important because that gives me what I want to do. So we want to minimize the amount of materials. So the amount of materials refers to how much material is used to make this box. So that will be the surface area. So we want to minimize the surface area of this box, and it's an open top. That's important because that means that it doesn't have one of the sides of this open top box. So remember, the surface area of a shape is the sum of the areas of each side or face, base, however you want to call them. So in this box, you have how many sides, right? We're going to have 1, 2, the one in the back, 3, that one, 4, and then the base is going to be the 5th side, just the way I've numbered them. It doesn't have a top, so no top, so that means no 6th side. Normally a box has 6 sides, so we need to find the area of all of those. So the surface area is, and all of these are, most of them are rectangles. We don't know, so let's give them some variables. So if we call that x, we don't know what the dimensions are, right? That's what notice what I highlighted. We want to find the dimensions of the box, so we don't know what the dimensions are. So, but we do know that we have a square base. So if this is x, then this is also x because it's a square. Now we don't know how tall it is. Here, the way that is drawn, it appears to be a cube, but we can't assume. So we're going to call this y. If it ends up being a cube, then it will end up being x, but we can't assume it. So it is xy. So if we're looking at the first side, so if I'm looking at this one, what is the area of that? Well, the area of this is a rectangle, so is x times y. So, and all of these are actually going, all the sides are going to have the same area, right? Notice that if I look at this one, the second side is also, the base is x and the height is y. So we have 1, 2, 3, 4 of those that are the same. So we have 4 sides of same area plus the base, and I'm going to say square base. So my surface area, and I'm going to get rid of the SA, and I'm just going to call it A, the area. So the area of one of those sides is length times width, so it's x times y, so it's xy, but I have 4 of those, so I'm going to have 4xy. So the areas, sides of same area is xy plus the square base, the bottom, and that is the area of a square is x times x, so you can also think of it as length times width, and the length and the width are the same, so x times x, which is x squared. So the area, I have 4xy plus x squared. Now this kind of gives us a problem, right? Because so I want to find the minimum of this, but why is this a problem? Why can't I find the minimum right now? And I can't do it because normally to find the minimum I have to take the derivative, but I have two variables, so that presents a problem. So my problem here is I have two variables, so that gives me a problem. We can't find the derivative. Technically, if you think about it, we really have three variables, a, x, y. So let's go back to the problem. What can I use to express this in terms of one variable? So we need to express the area in just one variable. So we're going to try to come up with what I like to call the helper equation. Something that's going to help us express the thing that we want to minimize, the a, in terms of one variable. So let's go back to the problem. What are we told that we haven't used? So a watch manufacturing firm needs to design an open top box. So we got that. That's how we got that we only have the square base. We don't have the top. The box must hold 32 cubic inches. So I haven't used that anywhere. So the 32 cubic inches is volume, right? Cubic inches, so your units tell you a lot about what you have. So I know the volume is 32. But what's the volume of a box? The formula for volume of a box is usually length times width times height. So in this case, then I'm going to have the length times width times height. So length is x times width is x times height is y. So I'm going to have x length times width times height is equal to 32. So x squared y is equal to 32. And so now I can see, I want to go back to my area here, and which one is easier to replace? I need to figure out, here I want to solve for x or for y to replace, to substitute into the area equation. And notice that I think it will be easier to replace y because y only appears once instead of x shows up twice. So I'm going to solve for y so I can replace just one y. So solve for y. So I have x squared y equals 32. So that means divide both sides by x squared. Y is equal to 32 over x squared. So now we can go back to the area equation. Notice that we say we need to express a in just one variable. Now that we have an expression for y, we can go back to our area. And so this is going to be 4x times y. Y is equal to 32 over x squared plus x squared. And so I was able to replace y because y equals 32 over x squared. So now I have the area as a function of the variable x. And distribute this. 4 times 32 is 128. So I'm going to have 128 x divided by x squared becomes x on the bottom plus x squared. And we want to find the minimum. So we need to take the derivative. Find a prime. So we're gonna, well, let me rewrite it. Since I need to find a derivative, I'm gonna rewrite it as 128x to the minus 1 so I can use the general power rule. So a prime of x is, bring the minus 1 down, so negative 128x to the minus 2 plus, bring the 2 down, 2x. And remember, we have to set these equal to 0 to find critical numbers. So I'm going to rewrite it again as over x squared. Right, rewrite it with positive exponents. And now I'm going to set it equal to 0 to find critical numbers. And solve for x. So here you can get a common denominator. So it's x squared. So I'm going to have negative 128 over x squared plus, I need to multiply this by x squared to get my common denominator. So I'm going to have 2x cubed over x squared equals 0. Right, so that gives me negative 128 plus 2x cubed over x squared equals 0. And you can think about cross multiplying or just multiply both sides by x squared. So negative 128 plus 2x cubed equals 0. And now solve for x. Add 128. So I'm going to have 2x cubed equals positive 128 divided by 2. X cubed equals 64. And take the cube root of both sides. So if I take the cube root of x cubed, I'm going to get x, and the cube root of 64 is 4. So x equals 4. So I only get one critical number. And we can use, in this case, my critical number is x equals 4. We can use the second derivative test. Or you can use the number line. But the second derivative test means we take the derivative of the derivative. So we had, this was the derivative, the first derivative. So if I take the second derivative, I'm going to get positive, what's that, 256. Negative 2 times a negative 120 is positive 256. X to the minus 3 plus 2. Right, which is 256 over x cubed plus 2. The second derivative test says if you plug in your critical number, so if I plug in 4, so plug in the critical number, I'm going to have 256 over 4 cubed plus 2, which is 256 over 64 plus 2. Again, we don't necessarily care about the value, but notice that this is a positive number. So if the second derivative is positive, that means that it's concave up at our critical number. So that means that A is concave up at 4. Right, so the concave up means it's curving upwards, and you have a critical number here of 4. So what sort of a thing is 4? It must be a minimum. Is that what we were looking for? Yes, right? It said find, going back to the problem, it says find the dimensions of the box that gives you the minimum. So yeah, we found the minimum. So x is 4. So now we have the dimensions. Because it's a square base, I know that's, so we just found that this is going to be 4, 4, and the height is going to be y. Well, y we found it to be right over here, 32 over x squared. Right, the height here is y, which was 32 over x squared. So this will be 32 over 4 squared, which is 32 over 16, which is 2. So the dimensions that will give us the minimum surface area will be a 4 by 4 by 2. So dimensions for the minimum surface area are x equals 2 and x equals 4 and y equals 2. So it will be a 4 by 4 by 2 box. And you could try to draw the box. So with the square base, I don't think I did a very good job here, but that will be 4, 4, and this will be 2. So those would be the dimensions. Now if you were asked for the volume, then the volume will be, well, we already know the volume is 32, but you can check it. 4 times 4, 16 times 2 is 32. If you were asked to find what is the surface area, then you would plug it into the area formula to get the actual surface area. All right, I'm gonna create another video for the other problem that we had in this example, which was the fence. So that'll be another video for that.